This video will illustrate the use of the upper limb plug-in-Gait compatible H2 upper limb kinematic model provided by Vicon. The first step would be to create a new database, if needed, using Eclipse. In this particular case, I will create a database within the D Vicon data folder, and we call it upper limb data capture. I will then use the clinical template.ini file for this particular database. Once the database has been created, I can open it, and then I will have to create the data tree for my data capture. So the first node, the top node, the patient classification node, will be called upper limb basic motions. The patient node will be called my subject, and the session node will be called my session. Once the database creation has been done, what I need to do is creating a new subject in Nexus using the upper limb plug-in-Gait compatible.vst file. At this point, the preliminary operation to run the model have been carried out, and the next step will consist in marking the subject up as shown in the figures on this video or in the documentation supplied with the model. For details on the marker placement, please refer to the documentation. Once the subject has been marked up, a static trial is needed to calibrate the medial epicondyle with respect to the upper arm tachycal reference frame, and also to calculate the glenohumeral joint center using a regression approach. So as you can see in the video, the data capture has been carried out and the reconstruction has been done. So at this point, the labeling of the markers needs to be done, and it needs to be done manually since this is a static trial and we don't have auto-labeling calibration yet. Once the static trial has been labeled correctly, a subject-specific auto-labeling calibration model needs to be created by running the calibrate labeling model pipeline, which has been already pre-saved and put there with the Nexus installation. This operation will create the subject's VSK file within the session folder. And you can see the calibration has been run successfully just because you can see all those colored boxes around the subject. After the subject calibration, the upper limb model needs to be run. The static part of the model will calibrate the medial epicondyles and calculate the glenohumeral joint centers. In order to do so, I will create a new pipeline and I will add the perform static body language modeling from the workstation operations section. Once the pipeline has been saved, as you can see in the video, and you can actually choose whatever name you like for that particular pipeline, I will just call it static body language model. I will now need to select the model that I want to run with this particular pipeline operation. In this case, it will obviously be the upper limb plug-in-gait compatible model that will need to appear in the active model list window. Running the model will then make the glenohumeral joint centers appear in the 3D workspace. As you can see in the video, there are 2 more points that have appeared after running the model. Another way to actually check whether the model has run correctly is to go and have a look at the subject.mp file, which is saved within the session folder. So as you can see from the video, I am now accessing the session folder, that particular database I'm working on, and open the subject.mp file, which is in the session. As you can see from here, those numbers there represent the local coordinates of the right and left medial epicondyle and right and left glenohumeral joint centers with respect to the upper arm technical reference frame. At this point, the static part of the model has been processed successfully, and everything is ready to capture and process the dynamic trials as well. As you can see in the screen, now the subject is performing some shoulder abduction motions. Since the subject-specific labeling model has been already created, the subject is also labeled in real time. So at this point, what you can also see is that the medial epicondyle marker has been removed from the subject, since it has been calibrated during the static trial. So now we are ready. I'm actually ready to capture some dynamic trials, and I'm going to do so. Once the trial has been captured, I can use the reconstruct and label function to have the trial automatically labeled for me. Before running the dynamic model, quality checks need to be carried out to ensure that the labeling has worked fine, and in case it has not, then I will need to manually edit the trial to make it usable for further data processing. In this particular case, what I'm going to do is manually label the sternum and wrist markers, since they are not completely labeled throughout the trial. Once I've done that, what I need to do is to fill the gaps within the trial, and I am going to do so using the fill gaps operation within the pipeline, limiting the maximum gap length to 15 frames, and then I'm going to delete the unlabeled trajectories. So at this point, the only thing that I'm missing is to filter the data before applying the dynamic kinematic model. So I'm going to do this by using the Waltering filtering routine and setting the options to have a 15 for the value of the mean square error. So once that have been filtered and cleaned up, now I am actually ready to process a dynamic model. In order to do so, I need to select a previously created dynamic body language model pipeline, select the right model to put in the active model list, and then process it. If the model runs successfully, there will be a group of new virtual points that the model created. These points are the points belonging to the anatomical three-dimensional reference frames associated with each segment of the model. You can also see that the medial epicondyle points have been recreated based on the technical reference frames formed by the upper arm markers. Also, once the model has run successfully, I can see under the subject's data tree that there is a new field called Model Outputs that can be expanded. By doing so, I will also be able to see the results of the model synchronized with the three-dimensional workspace. By selecting Graph and then Model Outputs, and then selecting the right shoulder angles Y, Z, Y, I am actually showing the right shoulder elevation. Another operation I might want to do for further processing is to export my data to ASCII format. In order to do so, I will have to select the Export Data to ASCII File Advanced plugin from the pipeline, and then put it in the active pipeline window. By accessing its properties, I will have to make sure that the marker file in the text box at the top of the options is the UL plug-in-Gait compatible.mkr file that comes together with the model file. Once the correct mkr file has been selected, I will be able to access all the outputs from the model. Let's say I'm interested in exporting all the joint angles. I can easily do that by accessing the angle section of the marker file, as I'm doing at the moment, and then moving all the angles to the right window by clicking the Add All button. Once all the variables needed have been selected, I will just run the plugin that will create a tab-separated file within the session folder named after the trial I'm exporting. So in this case, it would be shoulder AB adduction.txt. As you can see from the video, if you open the file with Excel, you will be able to visualize all the ASCII file for that particular trial.